Okay, good morning everyone. So today we are going to carry on with the drawing of the dot and cross diagram for simple molecules and covalent bonding. So just as a recap of earlier on what we have done. Okay, so earlier on we have looked at how to draw the covalent bonding dot and cross diagram for simple molecules. So I think the key message here really is this particular step whereby the number of electrons required equals to the number of electrons that will be shared. So you need how many, you share how many lah. Then don't forget things like your lesion, and then also after sharing, count how many are left with, put this outside lah. Okay, so and then another key thing is the structure formula. Okay, things like all these are the structural formula. So basically one line down here represents one covalent bond, okay, and one shared pair of electrons. Okay, so that's the key idea that day. So I look at a couple of examples starting from chlorine that day. So basically all these steps wouldn't be here lah. It's just there to guide you for the start. Okay, slowly we will move away from this step. Okay, so basically you have to write the electronic configuration. It's very important to plan first before you draw. Okay, then figure out based on the number of outermost electrons how many electrons each atom will actually share. We don't call them ions here, we call them atoms. Then once you figured it out, then figure out how many electrons is left with, and then reflect them outside the overlapping part. Okay, yeah, same goes for the water one. Okay, but when it's 3 atoms, I think that day the issue was this if you need to figure out who is in the middle. So usually the tip here is those who share most will be in the middle, right? Okay, then we come across more tougher examples, like for example diazine N2H2. Okay, where it's not easy to see who is in the middle. So this case is always better if you start out by drawing the structure formula. So the second method, so that day I actually proposed 2 methods. Okay, one method 2 is those easier one. Method 1 is usually for those tougher ones. You start with the structural formula, right? Okay, and also things like hydrogen peroxide, hydrogen cyanide. Okay, so today, okay, what we are going to do is this. Okay, let me go back to the answer copy. Okay, so today what we are going to do is we are going to look at structure formula, and then try to figure out the dot and cross diagram lah. Okay, so this will test your understanding of one line is equals to one covalent bond, which is equals to one shared pair of electrons. Pair means 2. Okay, so let's look at this molecule. It's called ethene molecule. You'll get to know it when we proceed to organic chemistry in Sec 4 lah. Okay, there will be more of these kind of things. Okay, so basically you can see out carbon there's 1, 2, 3, 4. So there's 4 bonds. So what you do is this: when there's 4 bonds, basically there's 4 shared electrons. Okay, so it looks something like this. If I were to draw it. Okay, so basically in this case for the shared electrons, 1, 2, 3, 4. Okay, likewise for the carbon on the left. Okay, also 1, 2, 3, 4. Okay, then the hydrogen being another element, I will use cross. Each of them will share 1, as you always know, right? So based on this, I think you can count around each carbon is actually 1, 2, 3, 4, 5, 6, 7, 8 electrons. Around each hydrogen is 1, 2 lah. Okay, then it will be correct. Okay, then after this, I'll put in my legend. Okay, so dot is electrons of C, cross is electrons of H. Okay, so the next one I'll probably have to bring in another symbol like a triangle for the oxygen or the carbon because it's 3 different elements. Okay, let's take a look at this. Okay, so this one is methanol, right? Okay, so I'll start off with the carbon. You can see there are 4 bonds, 1, 2, 3, 4 around the carbon. Right? Okay, so for this, the carbon in the middle is surrounded by a couple of hydrogen, followed by the oxygen. Okay, and then there will be another hydrogen here. Okay, so the hydrogen I will all use cross to represent their electrons. Okay, for the carbon, okay, I will use the dots. Okay, for the oxygen, I'll use perhaps this time around a triangle. Okay, a triangle. Okay, but it's important to take note of just now we never talk about the unshared ones. Okay, because all is shared already. Okay, carbon, as you know, okay, is 2, 4. So it's obvious here, already share 4, left nothing. Okay, then the hydrogen is 1, so share 1, left 0. Okay, so that's why I didn't reflect anything outside, okay, for just now. But over here, okay, the carbon, same thing, okay, share 4, left 0. Hydrogen is 1, share 1, left 0 also. Okay, but for the oxygen, you got to be careful. It's 2, 6. So this one share 2, because need 2 more to get a full outermost shell. Okay, then you left 4. Okay, so I got to reflect 4 triangles outside. Okay, let me go back to the oxygen. Okay, so my legend is this way. Triangle is electrons of oxygen. Cross is electrons of the H. And then dot is electrons of carbon. Yeah. Okay. Dot is electrons of carbon. Yeah, yes. Alright. Okay. Okay, right. Okay, so I shall go on. Okay, maybe you can take some time to absorb this. Pause the video, take some time to absorb this. I think the tricky part about this is figuring out based on the structure formula, figure out how many you shared. Then also remember the part that is unshared. Okay, you also need to figure that part out and reflect it in your dot and cross diagram. Okay, so going on, actually we got a lot of organic molecules. Okay, then the further examples, these examples will be interesting. Okay, I think this one particularly the one in part B is actually in your O-level 2019 database question. Okay, so because of that, I start going through this type of things. Okay, actually prior to that, I just stopped at page 28. That's it. Okay, I don't go on to talk much about polyatomic ions. Okay, so it's very special. This one a case of you got a bit of ionic and a bit of covalent bonding. Okay, these are very special. Okay, right. Okay, okay, let's look at part 3 now. Alright. Okay, part 3 is what we call ethane molecule. Okay, you got carbon. Okay, again, if you focus in you have 1, 2, 3, 4 bonds around. That means 4 shared pairs around. Okay, surrounded by your hydrogen. So all these actually you can see in real life using the ball and stick model, right? Okay, which when school reopens, I'll show you the ball and stick models. Okay, so I'm going to draw in all my electron shells first. Okay, so for the hydrogen one, I'm going to use cross. Okay, they always share one left, 0 hydrogen, very obvious. Okay, so write this part down so that you remind yourself how many is left with also. Okay, then carbon is 2, 4. So you will share 4 left, 0 so nothing will reflect outside the overlapping part. Okay, so for carbon I'm going to use dots. Okay, right, okay. So once you're done, just input your legends in lor. Okay, so legends, maybe I squeeze it here. This one is electrons. C dot is electrons. Wait, sorry, wrong. Dot is electrons of C, cross is electrons of H. Right, okay. Then this one maybe you can try yourself okay. Just to figure out how it looks like Alright, okay, it should be pretty simple for this one, okay. Because next one, I'm going to go into so this one I'll try and then I check when school reopen. Okay. Okay, so now I go into the next part. Okay, so all this is very interesting. You see a bracket, and then you see a structure formula. So this kind is all your polyatomic ions. Do you still remember them? Okay, like your carbonate, right? CO3 2 minus, NH4 plus. Okay, I think we talked in the Monday HBL about coming out with formulas, right? If I'm not wrong. So all these are polyatomic ions. So you better start making good friends with them. Okay, so you need to memorize them okay, for the purpose of writing chemical formulas. Right, so now we are going to look at them in terms of the dot and cross diagram. Okay, hopefully this gives you a better understanding of them. Okay, so they are very unique in the sense that these polyatomic ions you have both ionic and covalent bonds. I say this because some MCQ they ask you to pick options whereby that substance have both ionic and covalent bonding. So is this kind of case, the polyatomic ions case. Okay, so very important concept that you need to grasp over here. Okay, so there's some instructions, okay, of as to what must we do. Okay, on top of what we usually do for drawing dot and cross diagrams for covalent bonding. Okay, so just now what we did was this, right? Based on this, okay, it's obvious to us that there's one bond. It is obvious to us there's one bond. Okay, oxygen, chlorine. Okay, oxygen I will use dot okay, then chlorine I will use cross. Okay, so I need to figure out how many is left with. Oxygen is 2, 6. So based on 6, right? Okay, the 2 is nothing one okay, we just focus on the outermost. Okay, so you share 2 because 2 more to go to 8. Then you are left with 4. Chlorine is 2, 8, 7. So you share 1. Then you are left with 6. Okay, so chlorine I'll put 6 more outside. Okay, oxygen is the funny one. Supposed to share 2 okay, but down here you cannot force 2 because it's obvious it's only one bond. Okay, you cannot be try to funny and then put like that then it's wrong already. One bond is you can only have one shared pair of electrons. Okay, you cannot force one more in okay, it's not what the diagram has reflected to you. Okay, so we can't do that. Okay, then there's also this bracket that puts a minus. Alright, okay, so the instructions below if you have seen what I've written below is this. So you are supposed to add electrons to FO or N for negatively charged ions. Okay, so if it's like -1, then you add 1 electron to FO or N. It's like -2, then you add 2 electrons, like later on in the carbonate example. Okay, so this is your carbonate ion, in case you're wondering what am I talking about. Okay, to FO or N. Okay, so okay, let's explore this chlorate ion. This is a very interesting chlorate ion. Okay, a bit like your hydroxide. Okay, so now what I have to do is oxygen will be 7. Okay, you got to add 1 electron already. Add 1 electron, then it becomes 7. So basically, instead of sharing 2, it will be share 1. Alright, so it looks a bit like a group 17 element now. Okay, so oxygen now has 7, so it will only share 1. Yeah, so that day I think what's the mistakes that some of your seniors make was basically, so let it be 6, then share left with 5. Okay, so some of the mistakes that perhaps your seniors in that year did was this. Okay, I think the sharing part, okay, generally most can share 1 pair. Okay, then the chlorine no issue lah, according to what we usually learn. But the oxygen, I think they share 1, then they left 5 lor, which is wrong, because you only have 1, 2, 3, 4, 5, 6, 7 electrons around the oxygen. Okay, so take some time to digest this particular example. Okay, is something that is not what we usually do lah. Hopefully you won't encounter it even until your O levels. Okay, I would say this is on the tougher side. It is actually like a JC concept that they always like to put inside in the form of a database question. Yeah. Okay, let's look at the next one. Okay, it's a bromide ion, very unique. If you look at it, okay, bromine is, I know it's beyond the first 20, something 7. Okay, so based on this, you can see it actually shares 5 electrons. 1, 2, 3, 4, 5. 5 bonds around it. Okay, this one a bit more special, just for exposure's sake. Okay, then oxygen, this one, okay, so it's -1. So you have to add 1 electron to this oxygen. You notice not? Okay, this oxygen is a single bond oxygen. That means have 7 electrons one. Okay, just like the previous one. Okay, so this bromine surrounded by 3 oxygen. Oh, sorry, just now forgotten to put legend. Okay, where should I squeeze my legend? Okay, legend over here. Oh, sorry. Then just now I also !aiyo! So I should put dot for this one. Okay, so always check back. So this one is electrons of chlorine. Dot is electrons of O. Okay. Right, okay. Then let's look at the bromide. So this one you got to, okay, let's do the normal oxygen first. So oxygen I go by crosses. 2 crosses. Okay, so oxygen is 2, 6. We'll share 2, left 4. This is the normal kind of oxygen. Okay, same thing for this one, share 2, then left 4. Okay, but there's one oxygen where it becomes 7. Okay, this one, so you only share 1, left 6. This special oxygen is like 2, 7, so only share 1, left 6. A bit more like group 7. Okay, then now we go into the bromine. Okay, this bromine, will share one fair one in covalent bonding. The oxygen share two, he will share two back usually. Alright, then this one, there's a case whereby you don't have just for exposure. Later I'll show you. And share one. Okay, so bromine, is 7. So in this case, you already see it share 5. Quite unique. Normally only share 1, right? Okay, then you are left with 2. So put down here. Okay, this one is very unique. Okay, can go more than 8 already. If you notice, the number of electrons is already like 12 around bromine. Okay, so the third period and above one can have more than 8 lah. Alright, okay, but the more standard ones are like things like this okay, in V and VII. Okay, I shall look at the carbonate ions. Okay, wait, before that let me write the legend. Dot is electrons of bromine, cross is electrons of oxygen. Okay, so carbonate. Okay, so carbonate, you apply what you learn. Okay, so carbonate in this case, let's see. Okay, you have 2 minus, so you add 1 electron to this one. These two add 1 electron, then this one also add 1 electron. Okay, a bit running out of space. So maybe I draw at the bottom. Somehow like not enough space to draw over here. Okay, perhaps more space in your paper itself. Okay, so this carbon surrounded by 3 oxygen. Okay, so it's 2 minus. So it got covalent bond and it's like ionic. So normally ionic, for negative ions you add electrons in, right? So same thing down here lah. Okay, so okay, this one is the normal oxygen. Okay, the normal oxygen. Normal as in the 2,6 kind. Okay, then you will share 2 electron, then left 4. Okay, the other 2 is 2,7 kind. You will share 1, left 6. More like a group 17 element. Right. Okay, so this one is I'll use cross the normal oxygen. Then this is the 7 electron ones. Okay, right. Okay, so you do a check. All of them should have 8 electrons around them. So the legend is cross is electrons of O, dot is electrons of C. Yeah. Okay. Right, okay. So this one and the chlorate example is more standard lah. Okay, then maybe you can go back and just try this OH minus hydroxide. It looks a bit like the chlorate one. Yeah, you need to add 1 electrons to the oxygen. Okay, now I look at a more special one. Because usually now you share 2, the other atom will share 2 with you. Okay, but this case is not. Okay, let's look at ammonium lah. Okay, probably you won't get this. This is like the toughest of the 4. Okay, just for exposure's sake. Okay, so this one is positive. You notice it's positive for the first time. Okay, so if it's positive, what you need to do is take electron out from non-FO or N. So this one I will choose to take out from the top hydrogen. Take 1 electron, which makes it no electron. Hydrogen only got 1. Okay, so this nitrogen, okay, so you see this nitrogen, this fella is empty. Wait, Let me rearrange it a bit. Okay, so hydrogen all share 1. Nitrogen share. Okay, the remaining 2, because hydrogen 1, right? Okay, share 1, left 0. Okay, nitrogen, what you do is 2, 5. Normally you will share 3, right? Okay, but this case is quite unique lah, in a sense that it got to share these 2 also, because this hydrogen is empty. Okay, this one would be a very tough one. Okay, normally share 3, normally, but not in this case. Okay, very unique. Okay, there are always weird ones that I can show you. Okay, I won't test you this. Okay, this one I think a bit beyond you. Just sharing for learning purposes only. Okay, so this is dot is electrons of N, cross is electrons of H. Right, okay, I hope you are still surviving. Okay, it's a very tough first part for this video. Okay, now let's go into how does this simple molecules looks like. Okay, it's always better when I show you the model itself, when I see you back in class. Okay, but I need to complete this part then you will be able to complete your assignment 2B. Right, okay, along with some tough examples. Okay, this one is a O-level question. I think it's in 2021. Okay, no, this one is in 2021. The other one I think in 2020. Yeah, this one is in 2020. Yeah, all quite recent one. Okay, later on I share with you these few questions. Not easy. Okay, quite unique Sometimes it's not just content based. You need to look at information and then compare and then comment, whether it's accurate, those kind of things. Yeah. Okay. Yeah. So O level got quite a number of these kind of application kind of questions. Yeah. Okay. So never mind. Okay, now let's look at page 31, then 32, 33, 34. Okay. Hopefully you can cover covalent bonding in this video. That day was a bit very long. Okay, so structure of simple molecules. Okay, so most covalent substances that exist as simple molecules, except for the polyatomic ions got covalent, got ionic, right? I was telling you. Okay, so do take note of these exceptions. But most of them exist as simple molecules. So atoms in the molecules are held by covalent bonds. Okay, that means here, all these are actually the covalent bonds. Yeah. So, but the dotted line is actually the weak intermolecular forces of attraction. Okay, between school you say interschool, between molecules you say weak intermolecular forces of attraction. So make a guess, during melting and boiling, okay, which one do we try to overcome? Do we overcome the covalent bond, or do we overcome the weak intermolecular forces of attraction? So pause for maybe like 3 seconds, 5 seconds, think about it. Given that it's low melting and boiling point so you'll actually overcome the weak one okay. Alright, you can imagine this as two person that cross their arms. Okay, and then you have the hand with the little pinky connected to another person. So these two is like one molecule. Then another person, pinky to pinky cross the arm. So the pair always close the arm. Then they do pinky to pinky between here. This is another molecule. So here is always easier to break, right? You can imagine this way. If this is a physical lesson, I'll get like 2 pairs of students out to demonstrate this. Yeah. Or otherwise use the molecular models to show you all. Alright. Okay. So once we have established that, then we are clear. During melting and boiling, you actually overcome these weak intermolecular forces of attraction, represented by the dotted lines here. Okay, so most of them, because they are low melting and boiling point, right? Okay, you can imagine their boiling point is like 100 and below one. Okay, so H2O, some of them like CO2 is already gases at room temperature. So you can imagine they got negative boiling point like nitrogen, oxygen, all this. Okay, these are all the examples. Okay, so once again, if you refer back to what I mentioned that day regarding explanation of melting and boiling point, okay, you always need four things. Okay, structure. Okay, what kind of structure? Okay, so that day back to ionic bonding I explained this one to you, right? You need all this, correct? Okay, so go back to page 16 of what I mentioned earlier on. Okay, you explain melting and boiling, you always need these four things. Okay, so now I'll talk about is low, right? So small. Then weak intermolecular forces of attraction. Then particles is molecule. Then after that, structure, simple molecular structure. I always need these four things. Okay, so that's why I asked you to copy down this part. Very, very important. I put a heart shape, a star. Okay, you can be very sure I'll test you this in your mid-year exams. Okay, comparing the melting points of different types of bondings, and then looking at whether you are sure what kind of forces of attraction, what kind of particles, what kind of structure. Okay, you can be very, very sure. Okay, in fact, you should put 3 hearts around this. It's so important, this one. Alright, and you all always get confused. Okay, after a while molecules or ions, I think you also not sure about it. Okay, so I'll surely test you on this. Okay, so the structure, the forces of a, okay, sorry, actually I should begin with energy. Then number 3 after a while I will write FOA. Okay, forces of attraction. Then forces of attraction between what kind of particles. Okay, I always need these 4 points. No less, no more. Okay, always these 4 points. If not, you'll get penalized. Okay, I tell you straight first. Alright, okay, so you can see for this one, okay, I have number 1, this one, simple molecular structure. So I mentioned about structure, right? Okay, take off. Okay, I talk about structure already. Okay, number 2, small amount of energy. I talk about energy. Number 2, say, right? Okay, can take off. To overcome what? Okay, the weak intermolecular forces of attraction. Number 3, I talk about forces of attraction. And between what kind of particles? Okay, so number 3 I done already. Number 4, molecules. That's the particle. Okay. Alright, of course, some questions are a bit nasty. Ask you to compare. So end of the day, don't worry about this physical property explanation. I'll compile into a table for you to look across the 4 different kinds of bondings. It's always easier to revise that way. When you look across 4 and then differentiate between the 4. Yeah, it's always better that we do it that way. Okay. Alright, okay. So back to this on melting and boiling point. So sometimes the questions, they are pretty nasty. Okay, in the sense that they'll ask you to compare between molecules and molecules. So what you do in the event of that is that you larger the molecular size, stronger the intermolecular forces of attraction. Okay, and when that happens, you actually need more energy to overcome it. Okay, do jot this part down. Okay, between molecules. Okay, so I will still talk about structure. I will still then I compare the size. So one additional thing to do. Then talk about, as a result, bigger size, stronger intermolecular forces of attraction, FOA, and between the molecules. So you need more energy, right? So the same 4 things apply when you're comparing between simple molecule and simple molecule. Okay. Then for electrical conductivity, okay, for this case is basically poor conductor in all states, because molecules are electrically neutral. They are discrete molecules, so there's an absence of mobile ions or delocalized electrons to act as mobile charge carriers to conduct electricity. Alright, so they don't conduct because there's no mobile ions or delocalized electrons to conduct electricity. Okay, the third one, seldom ask you to explain. You just got to know that they are insoluble in water, soluble in organic solvents. What are organic solvents? They are things like oil and turpentine. Okay, generally insoluble lah, although some exception. Okay, the fourth one I add in because they do ask you questions on this lah. Okay, in O levels. Okay, so basically usually they are low density. Reason because they exist as gas at room temperature with this simple molecular structure. So they have very big volume, so lower mass per unit volume. Okay, so remember density is equals to mass over volume. So when you have a big volume, the density drop lah. That's why I say lower mass per unit volume. Okay. So relate to the formula. This is the cost. Then this is the you bring in the formula to explain the effect of this factor. All right. Okay, so bring in the cost, which is larger volume because they are gas already, right? Okay. Then how it affects in terms of the formula. Okay, that means with a bigger volume, you have a lower density, so lower mass per unit volume. The effect is this. All right. Okay, so the last part I basically bring in the concept of density lah to explain this. Although I mean in chemistry you seldom talk about density compared to physics ah. Right, okay. Right, okay. Let's take a look at this one. Okay, some of it I think like question 18 you already have it filled up in your notes. So you just listen to how I structure the question itself. Okay, it's important you have certain structure when you answer to structured questions. Alright, okay. So okay, so explain why oxygen has a higher. Okay, so this case is both simple molecules, so you got to compare the size. Okay, oxygen you know is like 2 6 hydrogen is 1. So you can see in terms of the size oxygen is actually bigger, right? Okay, because there's 2 shells okay, versus the hydrogen one there's only 1 shell. Okay, so oxygen is bigger. Okay, so same thing comparing melting and boiling point okay, I still have to talk about the structure one, no escaping this. Okay, then after that I will talk about the forces of attraction, okay, which I need to relate to the size of molecule in this case to compare. Okay, one additional task to do. Then between the molecules, okay, between what particles. Okay, then after that talk about the energy. Okay, so what I'll do is this, both got a simple molecular structure. Okay, so I've done structure, correct. Then I talk about they are helped by maybe I should add this word, intermolecular forces of attraction. Okay, no need. Okay, so number 2 number 1, number 2 okay, between the molecules maybe I add this one, between the molecules. Okay, this is point number 3. Then after that I will say they has a larger molecular size. Okay, okay, so link to point number 2 on this one. Then it will have a stronger intermolecular forces of attraction. So I do a comparison. Okay, then lastly the energy, larger amount of energy, okay, to overcome. Okay, then going to question 19 now. Okay, 19 is also a O level question actually. Okay, I think in 2019 or 2020 lah. Okay, but not a too tough one. So discuss the differences between the ways bonds are formed in Na2O as well as N2. So this one is a ionic compound. This one is actually a covalent one. Right? Okay, then so for this one you got to talk about losing and gaining electrons. This one you got to talk about the sharing of the electrons. Okay, so for sodium case, the ionic case, okay, your sodium is 281, so this one will lose one electron. Yeah, then your oxygen case, you will gain two electrons. Okay, so this one you form your sodium Na plus ion, this one form the oxide ions. Okay, then you also, as a result of that, you get your strong electrostatic forces of attraction. Then for the covalent ones, okay, you have nitrogen 2,5. So this one is obvious that you will share 3, then you're left with 2. Alright, you share 3, then left with 2. Okay, but I'll just talk about the 3 lah. Then as a result, you have a triple covalent bond. Okay, so when you do it, okay, it's important to structure it this way before you start attempting the question. Okay, so talk about sodium, lose one valence electrons to the oxygen atom to form sodium ion. Oxygen atom will now gain two valence electrons to form the oxide ion. So be clear about which one is atom, which one is ion. Okay, and then between the oppositely charged sodium and oxide ion, they now are held by strong electrostatic forces of attraction, FOA. Okay, so then in the covalent bonding side, okay, the nitrogen atoms share 3 electrons. Okay, and then they form a triple covalent bond. Okay, so that's how I structure this question 19. Okay, then let's look at the next one. Okay, on your ball and stick model and dot and cross diagram. Okay, this one is very interesting. I think 2 or 3 marks questions. Okay, I think 3, yeah, 3 marks question. Okay, so you have a dot and cross diagram, and then you have ball and stick models, okay, to represent a molecule of ethanol. So these are all simple molecules. Okay, so you are given in the table information about the lengths of the bonds in the molecule of ethanol and the atomic radius of each atom in ethanol. Okay, right. Okay, so now you have 2 pieces of info. Okay, let's look at maybe the dot and cross diagram first. Okay, so you got to compare against the real data when you're given the atomic radius, as well as the length of the covalent bonds. Okay, so first thing first, I think from a dot and cross diagram is that can you compare to the length of the bonds? Pause for a while and then think about it. Actually, does not, right? Does not show the bond length. Okay, but you got to be specific lah. The bond length of what lah? Okay, like your CH bond, your CC bond, the CO bond, the OH bond. Okay, all is not there. Okay, not able to see it. Okay, and then the atomic radius. Okay, then let's look at the atomic radius wise. Okay, this one I think to a certain extent it shows. Okay, because carbon and oxygen is bigger, right? If you compare to these two, it sort of show lah. Okay, so that's why for this one didn't comment. Okay, so sort of show the atomic radius. Okay, then now we go into the ball and stick model. This one, okay, let's look at the bond length. Okay, it seems like as though all of it is the same lah. Okay, to the when we look at it Okay, so this one all the bond lengths are the same Okay, although it's clear from the data. So this one you got to code data that your CC bond is actually the longest, right? 0.154 nanometer. Okay, so this one shows you the bond. Okay, but they're actually all the same, so not very accurate also. Okay, it's the longest. Okay, but it shows it all as the same length. Okay, and then for atomic radius wise, actually also the same issue. All of them actually have the same size. Okay, so all atoms have same size, when in fact actually your carbon atom is 0.077 nanometers, and then your oxygen atom is actually 0.073 nanometers. So they should be actually bigger than your hydrogen atom. Okay, 0.037 nanometers. Okay, right. Okay, so you can go model and do it, or my side I will go by the data side lah. Okay, to do it. Okay, either way is fine, so long as you cover the points. Okay, so dot and cross. Okay, so I say for the both dot and cross and ball and stick, it does not reflect the CC bond, the CH bond, the CC bond, the CO or the OH bond length. Okay, because bond length of your CC bond is the longest, but the bonds in the ball and stick models are actually all the same length. And then for dot and cross diagram, even worse, it was not reflected at all. Okay, so I sort of covered these 2 points already. Okay, yep. Okay, then subsequently, okay, I talked about the atomic radius. Okay, ball and stick model does not reflect the size of the carbon, oxygen, hydrogen accurately, because all got the same size. When the size of the oxygen, when the size of the carbon and oxygen atoms then you code the data is larger than the hydrogen atom. So coding the data, So there's a mark actually given for quoting data, if you realize. Okay, so some of y'all in your term checkpoint didn't really quote the data. Yeah, so you got penalized in the final question. Okay, so quoting data is important. All right, please remember to do this. Okay, especially in O-level questions, you're dealing with a lot of data in the tables, in the graph of this. Okay, you got to be able to quote them. Okay, so by doing this, this one I never say anything because it sort of show it. Okay, so this one is the one I emphasize more lah. In the ball and stick models, all the atoms have the same size, but in fact not lah. Okay, your carbon and oxygen, they are actually larger than your hydrogen atom, but it's not shown in this ball and stick model. Okay, so do pause for a while, okay, to analyze how I structure these questions. Okay, because sometimes when your first look at a new question like this, it's very new to you. You don't really know how to start. Okay, so go by the type of diagrams, the type of models, or like in the way I write it in red color is I go by the data. Okay, either way is fine. Okay, so long as you cover the relevant points, if you realize. Okay, so alright, the final questions on page 34 before we conclude covalent bonding. So next thing when you come back from the March holiday on Monday is I'll just check through whether you have fill up and whether you understood it. Okay, just do a quick recap, and then we'll go through your assignment 2B. Alright. Okay, so let's take a look at this tough, very tough, I would say, dot and cross diagram for urea. Okay, so in fact, how I came out with this, you are told certain things. Okay, like for example, new system for treating exhaust emission of diesel cars been developed. So they inject a fluid called the DEF, diesel exhaust fluid, into a. Okay, so it contains this thing called urea. Okay, urea, you are asked to draw dot and cross diagram. Wow, you stun, so many atoms, right? Okay, so the tip here is this. Okay, I have to use method 1, draw structural formula. Okay, which you will get very strong after you do organic chemistry. Your appreciation of this will get stronger. Okay, because in organic chemistry we keep on drawing structural formula. Okay, so much so it's like imprint inside your brain that carbon has 4 bonds. Okay, so carbon, let's just think about it. Nitrogen, carbon, oxygen, hydrogen. So normally this one is in group 15, so 3 bonds. Okay, so do refer to that chart down here to help you with your structural formula. Here, yeah, all these parts. Okay, so group 14, 4 bonds, group 15, 3 bonds, group 16, 2 bonds, and group 17, 1 bond. Alright, okay, let's take a look back at the urea question. Okay, very interesting urea question. So this is 4 bonds. This one 2 bond. And lastly, this is 1 bond. So the tip here, you probably do a few rounds of trial and error. So basically, usually the center one is the one that with the most bonds. Okay, then I think a few rounds of trial you might start doing things like this. Okay, then you realize, hey, might not have enough bond to go around. Okay, you might try to do this. You realize you might not have enough bonds to go around. Okay, let me see. Okay, you might realize, okay, you might do something like this. Alright, okay, but it's obvious to us that with that bracket the NH2 is together. Okay, let me erase this. Because at the start it might be things like this. You might start doing things like this, and then you feel very frustrated. Okay, but okay, so try to see from the formula given some hints that the NH2 is actually together. So C in the middle, then with the 2 NH2 this way. Okay, so the structure that we did just now, maybe some of y'all think possible but doesn't allow it to have 4 bonds on carbon, so that one also wrong just now. Look almost like as though we make it just now. Okay, so it's based on this. Okay, then I will start drawing So carbon, you can see 4 bonds so there's a legend down here. Dot is electrons of C. Cross is electrons of O. Then triangle is electrons of N. And open circle is electrons of H. Yeah, that's how I do it. Right. Okay, so start building up from the structure formula okay, and then understand that for nitrogen okay, you will share 3 pairs, right? 1, 2, 3. Okay, oxygen will share 2 okay, right? So nitrogen 2, 5, so share 3, left 2. So I put those 2 here okay. Carbon 2, 4, always most popular one, share 4, left nothing. Okay, likewise for hydrogen. Okay, likewise for hydrogen 1, share 1, left nothing. Okay, and finally oxygen 2, 6. Okay, so share 2, left 4. Okay, so the 4 are over here, 1, 2, 3, 4. Okay, all right, then I'm done. Okay, so sorry, suddenly it goes to the top of the page. Okay, ayo. Okay, so yeah, this is the one for urea. Okay, you can ponder over it over your March holiday. Okay, so homework for March holiday is your assignment 2B, which is your worksheet. Let me see it's worksheet what worksheet 8. Alright, your worksheet 8 Alright, assignment 2B. You probably have updated the content page. Yeah, yes. Okay, I'll upload the soft copy soon. Alright, so that's it for today's video.